So first of all, thank you very much for giving me this opportunity to present the work we are conducting in mines. And today I'm going to talk to you about our progress we've made about modeling reactive mail transport using MAGEMin. So just as a quick summary, I'm just going to present first a quick MAGEMin overlook, and then an introduction on the reactive transport, and then the approach of today that I'm going to present to you, which is the hash table, and like a very preliminary case study on Middle Ocean Ridge. So just as a background, so MAGEMin is the set of phase equilibrium modeling tool that we have been developing in mines. It's been now 6 years, and this is open source and freely available on GitHub. And there is like a complete documentation on how to use it and how to produce diagrams, but also export them for geodynamic models, for example. But presently, so MAGEMin, it's made of three main packages. The first one is the C code, which is basically like the computational framework of MAGEMin that can account for different thermodynamic database, the one of the thermocalc team, for example, but also the Stickstrud and Lithgow Bertolini database. But around MAGEMin, we have a Julia wrapper that allows to wrap every single function of the C code and to pilot them through the Julia interface, which makes it very modular and very efficient when we want to do some application and coupling with geodynamic models. And the last layer is the MAGEMin app layer, which is basically the user-friendly interface where we can do like some generic and common petrological calculations. So currently, the C code is MPI parallel, and it has been benchmarked one-to-one against thermocalc, at least for the thermocalc activity composition sets. So we have like the Julia wrapper and the graphic interface. In terms of single core performances, because that's what we are very much interested in mines, because our goal is really to have this direct coupling with geodynamics. At the moment, we are around between 10 to 150 milliseconds when we don't use initial guess. And this scales with the number of oxides and the number of solution phases, but also their complexity. In terms of performances, as soon as we have an initial guess, this drops down quite massively, and it goes down between 1 to 20 milliseconds. So just as a quick introduction on MAGEMin C, which is like the Julia interface here, just to show you how it works. So MAGEMin C, this is the programmable Julia interface to MAGEMin, and it allows you to do parallel calculation using multi-threading. And it's quite easy to use and to couple with geodynamic codes. For example, here, as soon as you have Julia installed, you can add a new package. And here you just have an example on how to perform a single point phase equilibrium calculation. So you simply initialize MAGEMin, providing a thermodynamic database. So there is a list of acronyms for this. Then you provide pressure temperature condition, an oxide system, the compositions of the oxides, and a system unit. And then you simply call the function. In that case, it's a single point calculation, single point minimization function. And then out of this will perform the minimization, and all the results of the minimization will be stored in a structure. Obviously, you can also provide arrays, so you can minimize a large number of points that will be parallelized, depending on how many threads you've load Julia. So there is a whole set of tutorials on how to use this part online. Just as a quick introduction on the app allows you to perform like a whole kind of different phase diagrams, which are pressure temperature diagrams, but also temperature composition diagrams and other kind of diagrams. You can extract all relevant thermodynamic informations. You can also do trace element partitioning, and you can also use some different kind of saturation models. There is also the possibility to do pressure temperature composition path, including now trace element modeling. And everything is done automatically. The labeling, also you can do some iso contour or isoplate, and everything can be exported as vector format files. And here, just to show you quickly, this is like out-of-the-box diagrams that were produced with MAGEMin, and all those diagrams can be directly exported as a lookup table for geodynamic coupling. In terms of ongoing development, so here I think for me it's important to say that MAGEMin is under very active development. It's relatively a very new software compared to the classical software that have been developed now for a very long time. And but for the last 3 years at least, we had more than 250 releases. So that's something that we actively work on. And at the moment, I am working on rewriting MAGEMin fully in Julia. And I expect to have it released by the end of the year. And this will come with an algorithm upgrade and a factor 5 of increase of performances. But this will also come with the possibility to have an arbitrary change of compositional space. At the moment in MAGEMin, we are restricted with the thermocalc way of formulating the solution phase model. And for some cases, it becomes quite tricky to boil down the number of components in the system. So we have to set them to low value, and that's annoying. So this has been solved, and this will come by the end of the year. This will also come with the possibility to add, modify, and calibrate existing solution phase models. And I also been working on implementing fluid speciation modeling, such as like in Enki for the deep earth water model and other kind of database. So, but today, what I would like to present to you is an application to reactive transport. So like everyone knows, today the Earth is a system in the reactive transport. And if you look at, for example, a mid-ocean ridge, we have the upwelling of the mantle that triggers partial melting and the formation of the oceanic crust. And as subduction goes, we have the release of the fluids that will hydrate the mantle wedge, generate magma that will eventually reach the volcanic system. So for all of those kind of special locations, we have systems that are in chemical differentiation that are dominated by reactive transport. Now the question is for us is how can we model such a reactive transport? And for this, we need mainly three components. The first one is the thermomechanical deformation, and for this we use usually viscoelastoplastic rheologies. We also need a component that will account for the two-phase flow, so the melt transport, the segregation of the melt, and finally, the topic at hand today is the thermodynamics, and we need to be able to compute the stable phase equilibrium. So, but the problem that we have currently is that stable phase equilibrium prediction in realistic systems. So in that case, let's take 13 dimensions. So one dimension will be temperature, the other one pressure, and the 11 others would be, for example, oxides. Presently with MAGEMin, we are around 15 to 120 or 150 milliseconds with an initial guess, and we go down to 100 and to 1 to 20 milliseconds with initial guess. So, but this is still rather slow, and we have been using several workarounds in order to be able to couple directly geodynamic modeling with petrological calculation. One of them is the lookup table, for which we have like a very large efficiency, but like a poor reactivity. So we cannot really model melt segregation using a lookup table unless we have just one component that will vary, for example, water. But the cool thing is that it's quite accurate and it's quite flexible. It's quite easy to create lookup tables for a whole range of different chemical systems. The other one is the parametrization. Here we have also a great efficiency, also relatively poor reactivity, but we have great accuracy, and the flexibility also is quite low because we need to recalibrate a model every time we want to change system. The other solution is the direct coupling, but it's quite slow actually, and but the cool thing is that we have the reactivity, accuracy, and the flexibility. The last option, that's something that is, I think, becoming quite important, is the surrogate models. For this, we have great efficiency, great reactivity, but we have some limitation actually on the accuracy and on the flexibility. If you want to update your surrogate model because you change some parameters in your thermodynamic database, you have to retrain the whole model, and that can be quite heavy. So the question is, how can we combine all those available approaches to make it more efficient? And here, the solution that I want to present you today is a mix between the lookup table and the direct coupling through what I call here a hash table. And the hash table will also provide and feed some initial guesses back to the direct coupling. So what is a hash table? That's basically a dictionary, and the idea is very simple, is that let's take a stable phase equilibrium for a given set of pressure, temperature, and composition. What you can do is round those numbers up to a certain level of accuracy. And from this, you can generate some unique IDs that you can turn into a hash. Then you create a database of hash that's basically like a tailored lookup table. And every time you have a bulk quark composition together with a pressure and temperature composition that are very close to an existing entry of the hash, it will round to the same ID, and you can pick up that pre-computed equilibrium directly from the hash. And if it does not exist, you have two alternatives. Either you do a full new thermodynamic equilibrium to compute a new hash from scratch, or you can use informations of hashes that are quite close to the original one to provide an initial guess. So, and to demonstrate this hash table approach, I'm going to present you like a very simple reference test model, which is based on the hydrous melting of a peridotite. And here I'm gonna use a very simple and simplified two-phase flow formulation, which is modified after Connolly and Podlachikov 2007. You have here some background parameters that we use, and we use what we call the decompaction weakening. It means that as the wave is rising, it becomes the solid host rock becomes weaker as the pressure of the fluid is negative. So here for this test model, we have a model duration of 10,000 years, and we have a petrological equilibration time of 500 years. In terms of thermodynamic database, here I'm using the igneous activity composition set of Green et al. 2025 with the full oxide composition. And here on the left, you can see a column of the reference model. This is basically like a section of the mantle that is 24 kilometers thick and 8 kilometers wide. At the top, the temperature is set to be 1190 degrees and the pressure at 2 gigapascal. And at the bottom, we have a temperature of 1310 degrees. So to start the porous wave, the melt ascent, I just add 2.5 weight% of water in the system. And just here, you can see how the model evolves in the reference case. So you can see like a porosity wave. Here on the left, you have the melt fraction in weight%. In the central diagram, you can see the evolution of the silica content of the melt as the porosity wave ascends. And on the right, you can see, for example, the Kleiner pyroxene weight%. Obviously, you have access to all the solution models and all their composition, but here it's just to demonstrate what the reference model looks like. So now the question is how efficient it is to use a hash table and how accurate it is. And here on the left, I was just, to demonstrate you, I was doing like the same simulation by doing the full calculation of the petrology. So I was computing for every point of the cell, the full thermodynamic equilibrium. And this diagram shows you the minimization cost per cell. So if you do the full petrological coupling, we get a minimization time per cell of around 100 milliseconds. Now, if we use only the hash, so without initial guess, we go down to 24 milliseconds per point. And now if we use a hash plus an initial guess, we have that value again, and we are around 13 milliseconds per point. Also, here on the right, you can see the kind of an example to show the accuracy. It's that between all of those models, we don't have major differences. So in terms of accuracy, we are quite close, either when using the full calculation or the hash model plus the initial guess. So now, an interesting thing is that we are creating a dictionary, so we are basically creating a database. So we can use the reference low-resolution model to create the database, and then we can feed that database to a higher resolution model. And when we do that, we can use and take advantages of all the calculation that were done before, so we can improve the calculation time per cell. And here, as you can see, as I increase the resolution, we go down to around 5 milliseconds per point for a resolution of 1600 per 480. Also, what is relatively interesting here is that we can now test the hash table approach and test the performances when we change the parameters of the physical calculation. So the two-phase flow models has different parameters that we can change to explore what will be the impact on the geometries or for example, the extent of the ascent of the wave. And in that case, I'm using the reference model as a starting database for all the other models. And like you can see for those three models, here are 5e-2. Here I just changed the decompaction weakening, and here also. So I increase it a little bit in those two cases. And here I increase the viscosity of the solid framework. And every time you can see that the wave travel to less distance, and the minimization time decreases. It basically means here in those two cases that the chemistry that is explored by the reference model covers the chemistry that will be explored by those three models. However, you can see on the last model where I decreased the viscosity of the fluid, that the porosity waves is going through the models already. And here we explore a chemical space that is larger than the one provided by the reference model. And therefore, we have an increase in computational time. So we had to perform new calculation from scratch. That's why the minimization time here is slightly increased. So just as a takeaway home for the hash table approach, that's a very simple approach that's very easy to implement. And the cool thing is that we have at least a tenfold increase of performances without a loss of accuracy. And also another cool aspect of it is that we gain an increasing efficiency as we increase the resolution of the model because we can rely on pre-computed hash tables. So now just to show you like a preliminary case study on a Middle Ocean ridge, I was just computing a few models several days ago, just to showcase how this kind of approach can be applied to a real case study. And the idea was to try to better understand the formation of dunites during Middle Ocean ridge partial melting. And so here on these photos, you can see like one of the most classical example of ophiolite, which is the Oman ophiolite. And on this picture, you can see like some dunite layers that are cross-cutting, so a depleted mantle, the Harzburgite. And one of the most accepted models for the formation of those dunites is the partial melting of the dry mantle below the ridge that creates some layers, dunitic layers, that then will coalesce as we have melt migration and pervasive transfer of the basaltic magma to the Mid-Ocean ridge. So here my idea was fairly simple. I wanted to study like a little window of this mantle, and for this I created a model that is 20 kilometers wide and 20 kilometers thick. And the pressure at the top here is set to be at around 0.9 gigapascal. And the temperature through the model is set up to be at subsolidus. So I just basically run like a phase diagrams to set the temperature at subsolidus everywhere in the model. In terms of composition, I use the KLB1 dry peridotite, and the resolution is around 240 per 240. And to start to initiate partial melting, I just provide a heat input of 100 degrees over 50,000 years. Sorry. So it's a little bit high, but here it's just to showcase how melting would work and how the porosity channel would form as the melting is ongoing. The total duration of the model here is 60,000 years, and as for the previous reference model, I use a petrological equilibration time of 500 years. And again, I use the igneous dataset of Green et al. 2025, but here I don't account for water, so the system is dry. And all the models that I'm going to present you, they've been running on 4 hours on my laptop. It's a Mac M3, so it's a good laptop, but it's still a laptop. So just to show you, I'm just going to present some GIFs. On the left, you can see the porosity evolution of the model, and the arrows represent the fluid flow. You can see several stages. During the first staging, you have the classical porosity channels that creates, and then everything starts to migrate and coalesce into like the biggest channel in the central part. And after a while, you could see that this channel is creating offshoot, right and left. On the right, you can see the evolution of the silica content of the melt that shows exactly the same patterns. And you can see that at the beginning of the model, when the temperature is low, we have the highest silica content of the melt, which is expected. And as the temperature rises, we decrease the silica content of the melt. So obviously, we can also display the evolution of the mineral content. On the left, you have here the evolution of the orthopyroxene content, and on the right, you have the evolution of the spinel content. It's quite interesting to see that in the region that partially melts, you tend to enrich at first in orthopyroxene. And then you create like the first channel. At the beginning, you could see that it was quite red, and then it becomes blue. So as you form those major channels, they start to lose their orthopyroxene and actually also clinopyroxene. And after a while, which is quite interesting in this model, is that the main channel locks and it creates offshoot. And then after a while, the second one starts to lock and the third one starts to develop. But I had to stop the model. It would be interesting to model further though. Okay. So now what we can do is track the olivine content. And as a function of olivine content, we can classify the rock types. And here you have in kind of you know, whitish color, you have larzolite, and in green you have harzburgite, and in kind of dark green you have dunite. Here it's quite interesting to see that in the first stage, you create so the first channel, which becomes first harzburgite, and then it converts into dunite. And after a while, there is an offshoot created on the right and the secondary offshoot on the left. Of course, those are very preliminary results. We didn't have really time to explore them further, but it was just to show you that the lookup table is the hash table is an efficient way to produce a reactive coupled model, so reactive melt transport models. And just as a last gift here, I wanted to show you the evolution of the hash table as we perform the simulation. So the dark blue are the new computation every time step. The light blue is the values that we directly pick into the hash table. So because we have a very close entry in terms of pressure and temperature and composition. And all the different shades of reds here represent different calculation used with various level of initial guesses. And just as a conclusion here, we can see that the hash table allows to have a very simple and efficient solution to perform reactive transport. And just with this very preliminary model, it can likely be used for a real case study. But of course, like at that stage, further work is needed, and it's really preliminary. So thank you.